So I really like to go camping. In fact, just yesterday I drove way up into the mountain to this super secluded spot. It was beautiful, super peaceful. I was really happy. But then I got a craving. I really wanted a beer, a burger, and a cupcake. And you might think that's impossible. You're way up in the middle of nowhere. Well, fortunately for me, just 40 miles away there's a cabin. And in this cabin live 3 of my friends. Albert, who's got an amber ale for me, Bertha with a bacon cheeseburger, and Cooper with the cherry cupcake. And the question, which is purported to be a Google interview question, although I'm not sure I believe that, is how quickly can my friends bring these 3 items to me, hanging out there at the campfire, if they're currently 40 miles away and have a bike that any 1 or 2 of them can ride at a time at a speed of 20 miles per hour, quite a bit faster than the 4 miles per hour that any one of them can travel on foot. So for example, Albert could take Bertha the entire 40 miles, drop her off, turn around, ride back the entire 40 miles to pick up Cooper, and then ride the 40 miles one more time to the campsite. The bike would be traveling continuously for a distance of 40 times 3 or 120 miles at a speed of 20 miles per hour, so it would take 6 hours. But as you can probably guess, that's not optimal. One way to speed up the process is to decrease the distance that the bike has to go by having Cooper walk during the time it takes Albert to drop Bertha off and come back and pick up Cooper. If we call c the distance that Cooper walks, maybe you can convince yourself that the bike travels 120 minus 2c miles. So 120 minus 2c all divided by 20 would represent the amount of time it would take. Because c is a positive number, this has to be less than 6 hours. I'm not going to bother calculating exactly what it is because that's not optimal either. Maybe this is a good time to pause. See if you can come up with this strategy that my friends could employ to get to the campsite as quickly as possible. I don't think the optimal strategy is obvious at all, so maybe a hint is in order.
To minimize duration, you need all 3 friends moving the entire time.
So maybe that's obvious, but it wasn't to me anyways, that the strategy that we just showed, where Albert starts by driving Bertha all the way to the end, can't possibly be optimal because Bertha spends the rest of the time standing still. So essentially we're wasting distance that she could have traveled. The way to get around that is to have Alfred drop Bertha somewhere short of camp and let Bertha walk the rest of the way. If we let B represent the distance that Bertha walks, and again use C to represent the distance that Cooper walks, a different distance than before, we can come up with this diagram representing the optimal strategy. At this point, you probably have 2 questions. 1, is your friend's name Albert or Alfred? And 2, how do we find B and C so that we can solve this problem? Well, to find B and C, let's just focus on the paths taken by Bertha and Cooper. Note that each of them walk some distance, B and C respectively, and ride the rest of the distance. Since they start at the same time and end at the same time, and have the same walking and riding speeds, they must both walk the same distance. So B is equal to C. We can solve for this variable by noticing that Albert Fred, whatever his name is, arrives at my tent at the same time as Bertha and Cooper. So the distance traveled by Alfred divided by his rate must be the same as the distance traveled by either of the other 2 divided by their respective rates. From the diagram, we can see that Albert traveled a distance of 40 minus c, then turned around, traveled a distance of 40 minus 2c, turned around again, and traveled a distance of 40 minus c. So Albert's total distance traveled is 120 minus 4c. For that entire distance, Albert was on the bike, so the rate was always 20 miles per hour. However, for Bertha and Cooper, it's a little bit different. They each walked a distance of c, because remember c is equal to b, at a rate of 4 miles per hour, and then rode the remaining distance of 40 minus c at a rate of 20 miles per hour. Because everyone arrived at the tent at the same time, the times are equal, so we can make an equation from the quotient of these distances and rates. To solve this equation, first clear the denominators by multiplying each side of the equation by 20. Then combine like terms and collect all the variables on one side of the equations with the constants on the other, and divide. Now that we know that both Bertha and Cooper walk a distance of 10 miles, we can plug in 10 for c in either of our 2 time equations to figure out that any of the 3 friends spend exactly 4 hours traveling from the cabin to my tent. So that's it? That's the answer? We're just over 4 minutes into the video. Is it really over? No. I got another question. You mean like the challenge question? No. This video, I'm going to ask 2 separate questions and then give the challenge question. Whoa, that's different. Can you do that?
Yeah, who gonna stop me?
Alright, so what's the new question? It's, what if there were 4 friends? We still need to travel 40 miles. The friends can still walk 4 miles per hour or ride a bike 20 miles per hour. We still have 1 bike, it can carry 1 or 2 friends. It's just now, instead of needing to get 3 people from the cabin to the tent, we need to get 4 people from the cabin to the tent. How long would it take? I bet you can come up with the strategy on your own. I mean, we kind of have the same constraints as last time, that in order to be optimal, we can't ever have anyone standing still. So everyone's going to have to finish at the same instant. So maybe we start by having Albert take Bertha to some distance, drop her off, and let her walk the rest of the way. We'll again let B denote the distance that Bertha walks. Meanwhile, Cooper and, Derek, sure, have been walking towards camp. Albert circles back and picks up Cooper at some point, at which Cooper has already walked a distance of C1 miles, and then transports him towards the tent, dropping him off even with Bertha, from which he'll have to walk another C2 miles to camp. Albert doubles back one last time to pick up Derek already having walked a distance of D miles, and rides him all the way to camp, getting there at the exact same instant that Bertha and Cooper arrive. That's a pretty intimidating diagram, and it gets even worse if you consider Albert's path. He first rode the bike a distance of 40 minus B to drop off Bertha, then rode back a distance of 40 minus B minus C1 to pick up Cooper, then rode back a distance of 40 minus C2 minus C1 to drop off Cooper, turned around and rode a distance of 40 minus C2 minus D to pick up Derek, and finally rode a distance of 40 minus D to the tent. Wow, that's a mess. So we have 4 different variables floating around, but we can clean things up if we just consider the paths of Bertha and Derek. Because each walks at the same speed and rides at the same speed, and they take the same amount of time to get from the cabin to the tent, they must spend the same amount of time walking. Therefore, B must be equal to D. Similarly, if we consider Cooper and Derek's paths, we can conclude that Cooper walks the same distance that Derek and Bertha walk. So C1 plus C2 must be equal to D. But unfortunately, that won't allow us to define neither C1 nor C2 in terms of D. It sort of looks like C1 and C2 are the same, but is that necessarily true? If I were back in school, I would say yes, and if my teacher asked me why, I'd say because of symmetry, which was kind of my go-to cop-out for problems like this when I couldn't really explain what was going on, but I had a pretty good hunch. In this case, it'll turn out that C1 is equal to C2. There's almost certainly a more clever way to prove this fact, but the way I got there is by going back to the 3-friend example. Recall that we solved for C by equating the amount of time it took the friend that always rode the bike with the amount of time it took a friend who walked for a stretch and then got a ride the rest of the way. If we wanted a more general solution for C, instead of assuming the distance from the cabin to the tent was 40, we could use a letter like M to represent how many miles apart they are. Going through the exact same series of steps, we'd eventually produce a similar equation which we could solve to see that C equals M over 4. In other words, the optimal strategy for 3 friends is to have one of them walk the first quarter of the way and have a different one walk the last quarter of the way. So how does that help us in the 4-friend case? Let me replay part of the animation and try your best to watch it but completely ignore Dexter. Note that Albert, Bertha, and Cooper arrive at the point labeled 40 minus C2 at the exact same instant. Furthermore, I claim they get there as quickly as possible because if there's a quicker way for them to get to that point, then they wouldn't be reaching the tent optimally. So really, this truncated portion of the 4 friends animation is just the 3 friends animation, where the total distance is 40 minus C2 instead of 40. So 40 minus C2 is M, and C1 is M over 4, so C1 is just a quarter of 40 minus C2. Similarly, when we reset the 4-friend animation, but completely ignore Bertha, there's a point when the remaining 3 friends all meet up at C1. From this point on, they act optimally to get to the tent, because again, otherwise the entire trip to the tent wouldn't be optimal. What that means is we can again use our general result from 3 friends, pretending that the distance is 40 minus C1, and the journey starts at C1. So M is 40 minus C1, and C2 is the distance from 3M over 4 to M. In other words, M over 4. So C2 is 40 minus C1 over 4. I know that's a lot to look at, but things are going to clean up real nice. If we take our 2 black equations and multiply by 4, we get that 4C1 equals 40 minus C2, and 4C2 equals 40 minus C1. So 4C1 plus C2 is 40, and 4C2 plus C1 is 40. So 4C1 plus C2 equals 4C2 plus C1. In other words, 3C1 equals 3C2, so C1 is just the same as C2. So that I can stop subscripting stuff, I'll use C to denote this distance. So the total distance that Cooper walks is 2C. And since we know that that's the same as the distance that Bertha and Derek walk, D is equal to 2C. From our black equation, 5C equals 40, so C must just be equal to 8, which tells us 2 things: that the picture wasn't drawn to scale, and that all of the friends except for Albert walked a distance of 16 and rode a distance of 24. So because time is distance over rate, and the walking rate is 4, and the riding rate is 20, It would take any of these friends 5.2 hours, or 5 hours and 12 minutes, to make it from the cabin to my tent. We can check this answer by calculating the time it would take Albert. He's always on the bike, so he has a constant speed of 20 miles per hour, and adding up the various legs of his journey, we see that he travels a total distance of 104 miles. 104 divided by 20 again gives us 5.2 hours as the optimal amount of time, and the answer to the question. That feels like enough for this video, but as always I want to leave you with a challenge question. This question might be a little predictable, but hopefully it's fun for you to work out. This week's challenge question is just, what if there were 100 friends? They still need to travel 40 miles, they still have a bike that can hold 1 or 2 of them, they still have a walking speed of 4 miles per hour and a riding speed of 20 miles per hour. What's the shortest amount of time it could take for all of them to get from the cabin to my tent? If you have any thoughts, questions, or solutions, I'll look for them in the comment section.